Have you ever really stopped to watch water moving? Like
Mm.
a river flowing or rainwater rushing down the street, even just water going down the drain. We see it constantly, but how does it actually work? Welcome to the deep dive. This is where we take a whole stack of information, could be articles, research, notes, you name it, and we boil it down to the key nuggets of knowledge you need to get up to speed fast. Today, we're diving deep into something called open channel flow. It sounds technical maybe, but stick with us. Our mission is to figure out how liquids move when they've got that free surface exposed to the air. We want to understand how they behave in different situations and why this seemingly simple thing is actually super important, both in engineering and just, well, the world around us. You might be surprised by some of this stuff. It could change how you look at water.
It really could. It's such a fundamental process in nature, obviously, but also in so many engineered systems.
Yeah.
And the physics behind it, it's surprisingly elegant, but also really critical to understand.
Okay, so let's unpack that. What exactly is open channel flow? What are we talking about here?
At its heart, it's pretty simple. It's a liquid flowing with a free surface that's open to a gas. And usually that gas is just air, at atmospheric pressure.
So the river example works perfectly. A stream. But you also mentioned things like sewer lines.
Yeah, exactly. As long as the pipe isn't flowing completely full, if there's air above the water, that's open channel flow too. That free surface is the defining characteristic.
And that free surface is important
Because it tells you what's making the water move. Unlike flow in a full pipe, where you often need a pump pushing it, open channel flow is driven almost entirely by gravity.
Ah, right. So it's the slope, the difference in elevation from upstream to downstream.
Precisely. That elevation difference provides the potential energy, and gravity pulls the water downhill. Of course, you've got friction fighting against it, slowing it down. It's that balance.
And it really is everywhere when you start thinking about it. Rivers, yeah, floods definitely, but also irrigation canals.
Drainage, ditches, gutters on your house.
Right, gutters. It's kind of amazing how common it is. Now, something you mentioned in the notes, the velocity isn't the same everywhere in the channel, is it?
No, not at all.
Mhm.
There's this thing called the no-slip condition. Basically, the water molecules right next to the solid boundaries, the bottom, the sides, they kind of stick, their velocity relative to that boundary is zero.
Like friction almost.
Exactly. It's due to viscosity. So the velocity is zero right at the edges. And interestingly, the fastest moving water isn't usually right at the surface. It's typically a little bit below the surface.
Huh. Why is that? Air resistance.
Partly air resistance on the surface, and also secondary currents within the flow can push the maximum velocity down slightly. It's complex, three-dimensional stuff in reality.
But for practical purposes.
For most engineering work, we simplify things. We talk about an average velocity across the whole cross-section.
Yeah.
And you know what? Treating it as one-dimensional flow, using that average velocity, it actually gives remarkably accurate results for a lot of real-world problems.
Okay, that makes sense. Now, how do we start classifying these flows? I remember seeing steady and unsteady.
Right. That's a key distinction. We'll mostly focus on steady flow today. Steady just means that if you stand in one spot, the depth of the water doesn't change over time.
Okay, so the flow rate might be constant. The depth at that point is constant. But it could be different depths upstream or downstream.
Exactly. The depth might vary along the length of the channel, but not moment to moment at a single location. That would be unsteady flow, like during a flood wave passing through.
Got it. And then within steady flow, there's uniform and non-uniform.
Yes. Uniform flow is the simplest case. The depth and the average velocity stay exactly the same as you move along the channel. This happens in long, straight channels with a constant slope and roughness. This constant depth is called the normal depth.
And non-uniform is just when it's not uniform.
Pretty much. The depth changes along the channel. And we split that further. There is gradually varied flow, GVF, where the depth changes slowly, smoothly over long distances. And then there's rapidly varied flow, RVF. That's where you get really abrupt changes in depth happening over very short distances. Think waterfalls, or flow around a bridge pier, or through a gate.
Okay, GVF is gradual, RVF is rapid. We'll definitely need to come back to those. Sounds like they're important.
Absolutely.
So we know what it is, we know the basic types. But how do we describe its character? Like, is it calm, lazy flow, or is it fast and chaotic? Is there a way to quantify that?
There is, and it's a really powerful concept. It's called the Froude number, usually written as FR.
Froude number.
It's a dimensionless number. Basically, it's the ratio of the flow velocity to the speed at which a small surface wave would travel in that water. For a wide channel, it's roughly v divided by the square root of g times y, where v is velocity, g is gravity, and y is depth.
Okay, the velocity compared to wave speed. Why is that ratio so important?
Because it tells you how information or disturbances can travel in the flow. And here's the really cool part. There's a direct analogy, a really strong one, to the Mach number in gas dynamics, like for airplanes.
Wait, really? Mach number like speed of sound stuff?
Exactly. The Froude number does for open channel flow what the Mach number does for compressible flow. It's the key to understanding the flow regime.
Okay, mind blown a little bit. So walk me through that analogy.
All right, so if the Froude number is less than 1, FR1, we call that subcritical flow, sometimes called tranquil flow. This is like subsonic flight, meaning small disturbances like ripples or waves can travel both upstream and downstream. The flow is slower than the wave speed, so waves can propagate against the current.
Okay, that makes sense for a slow river.
Then if the Froude number is exactly equal to 1, FR equals 1, that's critical flow. The flow velocity is exactly equal to the wave speed. That's analogous to sonic flow, Mach 1.
Right. And if Froude is greater than 1?
That's supercritical flow, often called rapid or shooting flow. This is like supersonic flight, Mach 1. Here, the flow is moving faster than the wave speed.
So disturbances can only travel downstream.
Precisely. Any wave or ripple you create is just swept away downstream. Downstream conditions cannot affect what's happening upstream in supercritical flow. It's a one-way street for information.
That's a fantastic analogy.
Yeah.
And that wave speed you mentioned, C0 equals square root of g times y.
Yeah, that's the speed of a small surface wave in shallow water. And notice, it depends on the square root of the depth y.
So waves travel faster in deeper water.
Yep. Surprising, isn't it? A ripple will move faster across a deep lake than across a shallow puddle, assuming the shallow water approximation holds.
You can totally picture that too. If you, toss a pebble into a really slow, deep part of a river, subcritical, you see ripples spread out everywhere, upstream and downstream.
Right.
But if you did it in one of those fast, shallow mountain streams, supercritical, the ripples would just get washed downstream immediately. You wouldn't see any move upstream.
Exactly. It perfectly illustrates the concept. And, you can even do a little experiment at home. Try running the tap water onto the middle of a dinner plate. Where the water first hits, it spreads out thin and fast. That's supercritical flow, FR1.
Okay.
But as it spreads out, it slows down and gets deeper. And you'll often see a sudden circular jump in the water level, a little ring where the depth increases quite abruptly.
I think I've seen that.
That's a hydraulic jump. It's the water transitioning from supercritical flow back to subcritical flow, FR1. It's a beautiful, tangible example of these flow regimes right there on your plate.
That dinner plate thing is brilliant. It really shows that sudden change, that jump. And that makes me think about energy. How does energy play into all this? You hear about the energy of flowing water, especially in floods.
Energy is absolutely central. We talk about something called specific energy, usually written ES. It's the total mechanical energy of the water per unit weight. And this is key measured relative to the channel bottom.
Oil tip to the bottom. Okay, so what energy are we adding up?
It's basically two parts. There's the potential energy due to the depth of the water itself, which is just the depth y. We call that the pressure head. And then there's the kinetic energy due to the water's motion, which we express as a velocity head, v squared over 2g.
So specific energy S equals y plus v2 2g. Depth plus velocity head.
Exactly, both measured as equivalent heights or heads of water.
And what happens if you, say, plot how this specific energy changes as the depth changes, assuming the flow rate stays constant?
You get a really interesting curve, a very revealing one. If the depth y is very, very small, the velocity v has to be huge to carry the same flow rate. So v22g becomes enormous, and the specific energy shoots up towards infinity.
Okay, shallow flow means high velocity, high specific energy.
Right. Now, if the depth gets very large, the velocity v becomes tiny. So v22g gets really small, and the specific energy s just gets closer and closer to the depth y.
So the curve starts high, drops down, and then goes back up, sort of.
Exactly. It drops down and reaches a minimum value, and that's where that minimum occurs.
Let me guess. Critical depth. We're the verifiable one.
You got it. The minimum specific energy occurs exactly at the critical depth, AIC. We call this minimum energy the critical energy.
Okay, that's neat. But what's really interesting is what happens away from that minimum point.
This is one of the coolest insights. For any value of specific energy that's greater than that minimum critical energy, the curve shows there are actually two possible depths that can have that same energy for the same flow rate.
Two different depths with the same energy. Huh.
On depth is on the upper part of the curve, where the flow is deep and slow. That's the subcritical depth. The other depth is on the lower part of the curve, where the flow is shallow and fast. That's the supercritical depth. They're called alternate depths.
Alternate depths. Wow. Can you give a real-world example?
Think about a sluice gate, like a barrier you can lower into a channel. Upstream, the water is usually deep and slow, subcritical. It flows under the gate, speeds up dramatically, and becomes shallow and fast. Downstream, supercritical.
Ah, so the deep upstream flow and the shallow downstream flow are alternate depths.
Often, yes. If you ignore the energy lost right at the gate itself, the specific energy just upstream and just downstream can be nearly the same, but the depths are completely different. One subcritical, one supercritical.
That's fascinating. And you mentioned engineers don't like being near critical flow.
Generally, no. Right near that minimum energy point, the curve is almost vertical. That means even a tiny change in energy can cause a huge jump or drop in the water depth. The flow becomes unstable, kind of unpredictable, so designs usually aim to keep the flow firmly in either the subcritical or supercritical regime away from that critical point.
Okay, that makes sense. Stability is key. Now, building on that, let's go back to those varied flows, GVF and RVF. You said GVF is gradual changes.
Right, gradually varied flow. The depth changes smoothly over long distances. The key to understanding how it changes, whether the depth increases or decreases as you go downstream, involves comparing the channel bottom slope, S0, with something called the friction slope, S7.
Friction slope, what's that exactly?
Think of it like this. It's the slope the channel would need to have for the flow to be perfectly uniform at that specific depth and flow rate. It represents the energy loss due to friction.
Okay, so you compare the actual bottom slope to this friction slope.
Yes, and you also factor in the Froude number. There's an equation, the GVF equation, that looks like didx S0 SF or FR2. Looks a bit scary, maybe.
A little bit, yeah. Didx is the rate of change of depth along the channel.
Right, and whether that's positive depth increases or negative depth decreases depends on two things. Is the bottom slope steeper or milder than the friction slope, the S0 SF part? And is the flow subcritical or supercritical, the 1FR2 part?
Oh, because 1FR2 is positive for subcritical flow and negative for supercritical.
Exactly. So the combination of the slope comparison and the flow regime tells you precisely how the water surface profile will curve. This leads to this whole classification system. Engineers call it the alphabet soup, M1, S2, H3 profiles, things like that.
Alphabet soup.
Yeah, there are letters for the type of slope. Mild, steep, critical, horizontal, adverse, and numbers for the flow zone relative to normal and critical depths. It gives you 12 distinct possible shapes for the water surface in GVF. Knowing which profile applies tells you if water will back up behind a dam or draw down as it approaches a waterfall, for instance. It's crucial for design.
Okay, so GVF is about predicting those smooth curves. What about RVF? Rapidly varied flow. That sounded more dramatic.
It definitely is. RVF involves abrupt changes over short distances. Think flow through transitions around sharp bends, or the classic example, the hydraulic jump.
Right, the dinner plate.
Yeah.
But let's talk about the real thing. What exactly is a hydraulic jump?
It's a really striking phenomenon. It's a sudden turbulent transition where a flow that is supercritical,
That's right, greater than one,
abruptly jumps up to become subcritical.
fry less than one. So it goes from shallow and fast to deep and slow. Very suddenly.
Very suddenly, yes. And the crucial thing, the absolute requirement, is that the flow coming into the jump must be supercritical.
Why? You mentioned this before, something about thermodynamics.
Yeah, it boils down to the second law of thermodynamics, really. Think about energy. A hydraulic jump involves a lot of turbulence, mixing, eddies. It's chaotic.
So energy is lost.
A significant amount of mechanical energy is lost, yes. It gets converted into heat, essentially dissipated by the turbulence. You can lose up to 85% of the mechanical energy in a strong jump. Now, if you tried to jump the other way, from subcritical, slow, deep, to supercritical, fast, shallow.
So you have to create mechanical energy out of nowhere.
Exactly. Which is physically impossible. It would violate the second law. So jumps only happen from supercritical to subcritical. It's nature's way of dissipating excess energy.
And that energy loss.
Yeah.
Sometimes engineers want that to happen. That seems weird.
It does sound counterintuitive, doesn't it? But yes. Think up at the water coming down a huge dam spillway. It's moving incredibly fast, it's supercritical, and it has enormous destructive power.
Right. It could tear up the riverbed downstream.
Precisely. So engineers often build a structure called a stilling basin at the bottom. Its whole purpose is to force a hydraulic jump to occur within that basin.
So the jump happens in a controlled way,
Ah,
dissipating all that energy safely within the concrete basin.
that's the idea. The intense turbulence chews up the energy, slowing the water down to a much safer subcritical velocity before it's released back into the natural river channel. It protects the dam foundation and the downstream environment. It's a fascinating use of what looks like violent chaos.
Taming the chaos. And you mentioned there are different kinds of jumps.
Yeah, depending on the upstream Froude number, jumps can look different. Some are nice and stable, called steady jumps, which are ideal for stilling basins. Others can be messy, like oscillating jumps that create waves which can damage structures. So engineers aim for specific types.
Okay, so understanding this helps us control the flow. How else do engineers control or even measure flow in open channels?
Well, control usually involves putting some kind of obstruction in the channel. We basically talked about two main types based on how the water gets past it.
Right, under or over.
Exactly. Flow under an obstruction happens with things like sluice gates. You lower a gate into the channel and the water has to squeeze underneath.
And it speeds up as it goes under.
It does. It accelerates, often reaching critical speed, FR1, right at the gate opening, and then becomes supercritical just downstream in the jet. It's kind of like a liquid nozzle.
A liquid nozzle, that's a cool way to think about it. And you mentioned drowned outflow.
Yeah, that's when the water level downstream is high enough to submerge the jet coming out from under the gate. When that happens, you often get a hydraulic jump forming right near the gate as the flow transitions back to subcritical. If the downstream level is low, you get free outflow where the jet shoots out into the air.
Okay, so that's underflow gates. What about overflow? Water going over something.
Those are generally called weirs. A weir is essentially a dam or obstruction that water flows over. The key principle is that if the weir is high enough, the flow passing over the crest is always critical flow, FR1.
Always critical. Why is that useful?
Because if you know the flow is critical, and you can measure the depth of water going over the weir crest, we call that the head, you can calculate the flow rate very accurately. Weirs are really common flow measurement devices.
Are there different shapes?
Lots. You have broad-crested weirs, which are like flat-topped dams, and sharp-crested weirs, which are usually thin plates. A really useful type of sharp-crested weir is the V-notch, or triangular weir.
Why is the V-notch so good?
Because the V shape means that even for very low flow rates, the water level in the notch, the head, is still reasonably high and easy to measure accurately. A rectangular weir might just have a thin trickle going over it at low flows, which is hard to measure. The V-notch gives you good sensitivity across a huge range of flow rates. Hydrologists love them.
Makes sense. Accuracy across the board. Now, there was one other odd thing mentioned, flow over a bump.
Yes, that's another specific energy puzzle. It's quite interesting if you have subcritical flow approaching a smooth bump on the channel floor.
Like a speed bump for water.
Kind of. If the flow is subcritical, slow, deep, the water surface actually dips down as it goes over the bump.
It goes down over a bump. That seems backwards.
It does. But think about specific energy. To get over the bump, the water needs to slightly increase its energy relative to the channel bottom under the bump. Since it's subcritical, the easiest way to adjust energy is often by changing depth. To maintain roughly constant specific energy relative to the original bottom, it trades some depth, potential energy, for kinetic energy, causing the dip.
Okay. Tricky. What about supercritical flow?
If the flow approaching the bump is supercritical, fast, shallow, the water surface actually rises as it goes over the bump.
So the opposite happens. Why?
Again, it's juggling depth and velocity to manage the specific energy. In supercritical flow, it's often easier to increase depth slightly to get over the bump while maintaining roughly constant specific energy. It all ties back to that specific energy curve and the two alternate depths.
These subtle effects, like the water dipping over a bump, they might seem, I don't know, academic. But you mentioned they have huge real-world consequences, and the big one you highlighted was bridge scour.
Absolutely. Bridge scour is arguably one of the most critical life and death applications of open channel flow principles. It's the #1 reason bridges fail in the U.S.
Number one.
Yeah.
Wow. And it's just erosion?
It's erosion, but it's driven by complex flow patterns. When floodwater flows past a bridge, pier, or abutment, the obstruction causes the flow lines to concentrate and often forms a powerful swirling vortex, like a tornado turned on its side right at the base of the pier.
A horseshoe vortex, you called it.
That's the one. This vortex acts like a drill, digging down into the riverbed, lifting sediment away, and creating these deep holes right around the foundation.
And if the hole gets deep enough,
It undermines the foundation, and the bridge can collapse. Tragically, this often happens during major floods when the bridge is needed most.
and the faster the water, the worse the scour.
Definitely. The erosion rate is strongly linked to the velocity of the flow hitting the pier. Faster water, more turbulence, stronger vortex, deeper scour hole. It's a direct consequence of the flow interacting with the structure.
So protecting bridges is a massive challenge. You mentioned riprap, just dumping big rocks isn't always enough.
During major floods, the forces are just immense. Water can move incredibly large boulders. So while riprap helps, engineers are constantly researching better ways, things like specially shaped piers or installing underwater veins to guide the flow more smoothly around the foundations, trying to weaken that horseshoe vortex.
It's really sobering. All this complex physics we've been talking about, Froude numbers, specific energy, varied flow, it directly impacts safety and infrastructure in such a fundamental way.
It really does. So, we've gone from just watching water flow to seeing this intricate interplay of gravity, friction, and energy. We've seen how a simple dimensionless number, the Froude number, can classify the whole character of the flow.
Yeah. And how energy behaves in unexpected ways, like with alternate depths,
Yeah.
and how engineers have learned to work with it, sometimes dissipating it intentionally with things like hydraulic jumps.
From the tiniest stream to the design of massive spillways and the safety of bridges, it all comes back to these core principles of open channel flow.
So next time you're out, maybe crossing a bridge, especially if the river's running high, or even just, watching the water in a gutter after a rainstorm,
Yeah.
take a second. Think about those unseen forces, the gravity, the friction, the energy playing out. What other hidden fluid dynamics might be happening right in front of you?
Hopefully, this deep dive has given you a new lens to look through, a new appreciation for the water all around us, and the really quite beautiful physics that governs how it moves.